Hello. This CERTIP project, ER18-1063, examined resin-based sorbent technologies for the sustainable treatment of per and polyfluoroalkyl substances, or PFAS. This was a collaboration between the Colorado School of Mines, Arizona State University, and CDM Smith. The overall goal of this multifaceted project was to identify the most sustainable and cost-effective resin-based technologies for treatment of AFFF impacted groundwater. We applied experiments in combination with systems-level modeling to meet several objectives, including identifying resins that meet multiple criteria, including absorbing the widest range of PFAS as possible, potentially being regenerable if appropriate, and having minimal influence of non-target constituents. We also aim to identify optimal resin regeneration and concentrate management options, including assessing two promising technologies for destruction of PFAS in liquid concentrate streams. And finally, we applied life cycle assessment and life cycle costing methodologies to evaluate process sustainability and costs for different treatment design decisions. Addressing our objectives, the project first identified resin properties, PFAS chemical properties, and water quality conditions that influence PFAS absorption to resins. Results from the work found that detailed in this project and this project report and a number of peer-reviewed journal publications showed that PFAS absorption to resins is highly dependent upon both resin characteristics and PFAS chemical structure. Anion exchange resins were found to be much more effective in absorbing PFAS than either cation exchange resins or non-ionic resins. Polystyrene-based anion exchange resins being marketed as PFAS selective single-use resins were found to be optimal, absorbing PFAS much more strongly than conventional regenerable resins based on either polystyrene or polyacrylic matrices. Both strong and weak-based resins were found to be effective, and the extent of PFAS absorption was influenced by the counterion preloaded on the resins. Finally, findings from field pilot testing of different resins were consistent with the performance observed in laboratory settings. In examining regeneration of anion exchange resins, we found that effective desorption of PFAS and resin regeneration requires both salt brine and alcohol cosolvents. Some trade-offs were observed between the required concentrations of these two components to achieve successful regeneration. Regeneration efficiency was also improved when using more hydrophobic alcohols like propanol in place of methanol. And weak-based resins cannot be regenerated by pH adjustment alone. And resins marketed as single-use resins can be regenerated, but it typically requires higher cosolvent fractions than the regenerable resins. One major need for sustainable management of regenerable ion exchange systems is technologies for effective destruction of PFAS that accumulate in the waste brine byproduct of resin regeneration processes. Experiments in this study demonstrated that this can be accomplished by leveraging electrochemical oxidation and hydrothermal alkaline treatment technologies being developed in other CERTIP-funded projects. Electrochemical oxidation, or ECO, applies potential sufficient to promote oxidation of PFAS at cathodic surfaces, including boron-doped diamond. Tests here found that ECO can effectively defluorinate PFAS with rates being dependent upon brine composition and the presence of dissolved organic matter and residual cosolvent. Tests with hydrothermal alkaline treatment, or HALT, were conducted with an ion exchange still bottom sample obtained from an actual Department of Defense field pilot study. These experiments showed that HALT degrades and defluorinates all PFAS detected in the still bottoms sample. Finally, life cycle assessment and life cycle costing analyses were applied to address sustainability and costs of resin-based treatment systems. These systems-level analyses quantifies sustainability and costs of PFAS treatment over the entire life cycle of the treatment system and can include construction, operating, and deconstruction phases. Here, we compared ion exchange with granular activated carbon adsorption systems, as well as comparing different options for managing regenerable ion exchange systems. This helped us to identify the most sensitive design variables and site-specific factors. Media replacement or regeneration frequency was found to be the major determinant of costs and environmental impacts, a factor that also was found to be highly sensitive to the PFAS treatment criteria that will be used for site remediation activities. Additional details of all this work can be found in the project report, also posted on the CERTA project webpage.